Okay, so friction. Let's just talk a little bit about the idea of friction and what things affect friction, and then after that we'll do some calculations that should enable us to work it out. So the key thing is that friction is a force which opposes motion. So whichever way something is trying to move, friction is pushing the other way. So let's get a disc out the front here that we can use. Okay, so object, it's going to move on the disc. Okay, so if I'm pushing it this way, friction is going that way. Yep. And if I give it a bit of a shove, see, something's got to stop it. Because Newton's laws say that if there's no forces acting, it'll keep on moving at a constant velocity. And it doesn't, does it? You can all see that. As soon as I give it a bit of a shove, as soon as I let it go, it slows down. So there must be a force going that way, causing an acceleration that way. So friction acts towards the door. And conveniently, if I turn around and push it this way, friction will turn around as well, which is just as well, because imagine if the rule was friction always works towards the door. And then as soon as I touch this, even that much, friction would start going that way, it would accelerate, more friction, more acceleration, more, and it would be out the door and through the wall over there before anything happened, okay? So friction always goes against the motion. So as soon as I push it this way, friction's now going back that way, okay? So that's the key thing. So whenever you're doing one of these calculations, draw a diagram, say which way your thing's moving, and friction will always be going the other way. That's thing number one. Okay, the second question is, what do I do with my whiteboard marker? See, that could be the third question. Okay, so the second question is, which things affect friction? So it's a force which opposes motion, affected by, so I'm just going to make that, is it A or an E for effect? I'll go for one of those Greek AE things. There you go. Because I can't spell. So affected by. Okay. So which things affect friction is the question. So what's going to determine how big the force that's pushing back against this is? So I give it a shove. It slows down. What's affecting the size of that force? Surfaces. Okay. So it's affected by definitely what the surfaces are made of, absolutely. And you can look up online, you Google friction between surfaces, go to a website like Engineering Toolbox. So it's just all one word, engineeringtoolbox.com, and it's got all lists of data, and you can look up what is the friction between concrete and steel, or between steel and steel. It's all there. So definitely what the surfaces are made of, absolutely, that affects it. What else do you think is going to affect how quickly this thing slows down? Yep, so the force is going to affect the acceleration. So you mean the force of friction going this way? The force, how fast I shove it. So how fast I shove it is the initial speed. So does the speed affect the friction? So if it's going faster, does it have more friction? There is a point, there is a thing called, which we're not really going to talk about, but there's static and kinetic friction. So the amount of friction it experiences when it's still is different from when it's moving slightly. So you can demonstrate this. So this is going to give us a force. Once it starts to move, so it's got a certain amount of friction now, that friction is enough to keep it held, still enough to keep it held, still enough to keep it held. Okay, once it's moving, I can actually bring it down a bit and it'll keep on moving. Yeah? So the force to keep it moving is less than the force that needed to get it moving. Yep. So the static friction, the force when it's stationary, is a little bit more than the kinetic friction when it's moving. But pretty much once it's moving, the friction, it doesn't really matter how fast it's moving, the friction is pretty much the same. Okay, so there is that concept which think about. So the key thing so far we've got is what the surfaces are made of, the mass of this object. Okay, so this is a heavier thing. So if I do this and then try and push it, it's a lot harder than if I'm not doing that. Okay, so it's being squashed down into the surface, it's harder to push. So the mass of it, which really what we mean is the weight. Yeah, because it's the amount of force it's pushing down with. Yeah, so it's the weight of the object. Yeah, so the weight of the object, or really the force between the surfaces. Yeah, it's definitely going to make a difference. So when we come to work on these things, we're going to draw some diagrams. We're going to definitely want to put the weight and the reaction force of the surface. That's going to matter. Absolutely, it's going to matter. Any other ideas of things that you think might play a part? The angle, the slope, yeah. So the angle, when I did the angle thing, it provided a force effectively. So weight was effectively, if I made a really steep angle, that's quite a steep angle, yep. And now if I go, all of the force is downwards, yeah, and it's not being held onto the disc at all. So if I let it go, effectively friction, there's no effect, it just falls down. Whereas when I had it flat, there was no weight that was trying to move it, all the weight was pushing into the disc. And when I've got it somewhere in between, some of the weight's pushing into the disc and some of the weight's providing motion, yeah. So the angle isn't actually affecting the friction, it's affecting how much of the weight of the book is push and how much is push. Yeah? Which is why when we come to do calculation, oh no, I should put this down, it's kind of hard to see if I leave it up. When we come to do any calculations with these things, whenever we've got a slope with something on the slope, yeah, weight acts downwards. Doesn't matter what the slope's doing, the weight still goes straight down. And the reaction of the slope is always pushing at right angles to the slope. We call it the normal force. So the reaction up here is a normal force or a reaction. And when we want to compare these things, it's much, much easier if we break the weight up into bits. Okay? So up until now, when you've done components, you've always done horizontal and vertical components. Okay, what's happening horizontally, what's happening vertically, da-da-da, work it out. As soon as you get things on the slope, it's much, much easier mathematically, and it makes sort of sense if you talk about, I can spell that word, components parallel and components perpendicular. Okay, because effectively you're saying the parallel bit is the bit where the weight is acting to push it along, and the perpendicular bit is where the weight's acting to hold it on the surface. Okay. And those are the two things that you're interested in, rather than what's going down and what's going along. Because going along is sort of trying to drift it off into space, and that's not really likely to happen. And if I have my book on my desk on a bit of slope, it ain't going to go vertical. It's never going to leap off in that direction. It's going to go down the surface. So I'm really interested in what force is pushing it down the surface and what force is pushing it into the surface. Okay? But the actual angle doesn't affect the friction. It affects the force, which in turn affects the friction, but it's not the angle itself that affects the friction. Yep. There's one other one that people normally go, oh, what about? Which doesn't actually affect it. You've got the two that matter, but people usually go, surface area. If I've got a bigger book or a smaller book, it'll make a difference. And actually it doesn't make any real difference at all. If we go for where's the point where it just starts about there? If I have the same, it goes about the same speed, we hold it Where's the starting point there? About there. Compared to on the flat, it's about the same place. Yeah, given that that side is what? A quarter of that side? The difference between them is experimental rather than, it's not 4 times bigger or anything like that. Yeah? So the area between the two, between the things isn't really a major factor. So these are the two things we're worried about: what the surfaces are made of and what force is going on between the surfaces. Okay. And we have a formula that demonstrates that. So we need a number for what the surfaces are made of, and the number we're going to use for that is mu. Well, the letter is mu, which stands for coefficient of friction. Okay, and that you look up on Engineering Toolbox or some equivalent website, which you can't do in your exam. Old-fashioned actually, they don't let you have the internet in your exam. So they give you a bit of paper with ones that you might need. So in the exam, there's a formula sheet that has some coefficients of friction. So coefficient of friction is definitely one thing we're going to worry about. And the second thing we're going to worry about is the force between the surfaces. And as I've drawn here, if the surface is on the slope, it's the right angle force. And I'm going to call that N for normal. So the force at right angles to the surface, which if it's flat, is exactly equal to the weight. But if we're on a bit of a slope, it's not. And then we have a formula that ties these things together, and it says that mu equals FF divided by N. Okay, so FF is force of friction, and that's on your formula sheet for this paper. Okay, so the coefficient of friction is force of friction divided by the normal force. Or if you rearrange that slightly, you get force of friction is mu times N. Okay, so whatever friction there is equal to this coefficient of friction times N. And let me just get your head around this thing properly. Coefficient of friction is a number, no units, which makes sense because that's going to be in newtons and that's going to be in newtons. Newtons over newtons cancel out, so there's no unit left, so it's got no unit. Between 0 and 1. Okay, so 0 means no friction, so as soon as you push it, it'll just keep on moving. There's no force opposing the motion, so if I started at 1 meter per second, it'll keep going at 1 meter per second. 1 means that the force that's pushing against it, friction, is exactly equal to the weight of the object. So it's just as easy to do that as it is to do that. Okay? And obviously it can't be more than 1, because if it's more than 1, you basically lift the whole thing and move it. Yep? So coefficient of friction is a number between 0 and 1. Yep? So if you do a calculation in an exam and your mu comes out to be something other than between 0 and 1, you've stuffed it up. And go and try and find something else to do it with. Okay? So that's the ideas behind friction, how we're going to measure it, and the equation that we're going to use.